Whenever we talk about chemical reactions or administering drugs or developing a new soap, the solubility of molecules is enormously important. Understanding solubility starts with understanding a previously mentioned intermolecular interaction, which is one that is based on dipoles. Dipole-dipole interactions occur between molecules that have a permanent dipole. Now, how do we determine if a molecule in fact has a permanent dipole? We need to do a couple of things. The first one is to know the three-dimensional structure of that molecule. We can do that using Lewis theory and VSEPR theory, which we've discussed in a previous video. Once we know the three-dimensional structure of a molecule, we have to determine if there are chemical bonds between two atoms in that molecule that are polar. Polar here means that they have a large difference in electronegativity. Let's take this molecule here. This is a molecule called dichloromethane. It's methane with two chloride atoms instead of hydrogens. Chloride is a very electronegative element. It's much more electronegative than carbon, and therefore the difference in electronegativity between carbon and chloride is large. This means that the carbon-chloride bond is polar. When we draw the three-dimensional structure of this molecule, we can quickly figure out that these two polar bonds point to one side of the molecule. That means that these polar bonds don't cancel each other out. Combined, this means that this molecule has a permanent dipole. There is a very simple principle to predict what sort of solvent will dissolve what sort of molecule. It's known as like dissolves like. Polar molecules will dissolve more easily in polar solvents. Apolar molecules dissolve more easily in apolar solvents. We can consider a polarity scale. Water is generally considered the most polar common solvent. On the other side of that scale are very apolar compounds such as oils. For example, decane is an oil and it's very apolar. When we then have two somewhat similar molecules, we can try to predict their relative solubility in water. Here's methane and here's dichloromethane, which we discussed in the previous slide. Dichloromethane has a permanent dipole moment of 1.6 dBi. Methane has 4 hydrogen substituents. It has no permanent dipole. This makes methane very apolar, making methane very poorly soluble in water. Dichloromethane is almost 1,000-fold more soluble on account of its increased polarity.